Alright, so I'm not going to do the physics of this any justice. I'm just going to give you a very brief overview in one line. If you are interested, I encourage you to review your waves from physics. But basically, human hearing is frequency dependent, and we can detect sounds ranging from 20 hertz to 20 kilohertz. And sound acts as a wave traveling at 350 meters per second through the air medium. And we can pick up on any small disturbance to the overall pressure, to the overall atmospheric pressure. That's how we detect sound. And we can define the sound pressure in decibels. Okay? And is going to be defined this way, where you have a root mean squared pressure in pascals divided by 20 times 10 to the minus 6 Pascal, which you can redefine as P over P naught. P naught is the threshold pressure below which your ear cannot detect any disturbance. And the root mean square is going to be the amplitude of the sound wave traveling across the air divided by the square root of 2. Okay? And the amplitude may be obtained from a coefficient of the sine wave, and our hearing will be cited detecting between 0 decibels at 1 kilohertz. So that's as much as I want to go over the physics of hearing. If you have any questions, please raise them to me. I will explain gladly. But that's basically some of a quick overview, because I think you've all seen this before. Now, human hearing, and why we actually care about this is because we're talking about worker safety. So we need to figure out whether the hearing will be affected by any noises in a chemical plant or in a process. So human hearing is not linear, but it is actually logarithmic. So it's logarithmic. So the ear is more sensitive to sounds with higher frequencies. And you probably know from your own experience that it's possible to eliminate low intensity sounds through the use of louder sounds. So let's say, for example, you're trying to sleep and someone's snoring, you can blast white noise and drown that out if it's louder than someone snoring, right? And that just has to do with the fact that the louder sound affects your hearing more, right? And in order to determine the effective frequency or decibel that you're going to be hearing, one does not simply add them up, but has to take a logarithmic addition system. So the equivalent decibel that your hearing will pick up in decibel from a variety of sources will be 10 times the log of this sum. So this is just dependent on how many sources, sound sources you have, and what their individual decibel levels are. So Li is the individual decibel sound level for each for sound source. Okay, so and the equivalent is what it would be for a variety of them. All right, so you can easily apply this, and I challenge you in the homework to do so. And I will let you know that if the higher the number is, the more it will affect, the more it will skew the equivalent. So if I have a variety of sources and one of them is at 100 and the other ones are at like 20 and 10 and maybe 5, the equivalent is going to be much closer to 100. It's not going to be just an average of 5, 10, 20, and 100. It's going to be much closer to 100 due to this relation, and it's going to be pretty close to the way we actually hear and interact with sound. Okay? OSHA recommends that for a typical 8-hour working day, 90 decibels should be used as a limit to prevent both discomfiture and ill effects on workers and the environment. So in the case that if you exceed 90 decibels, what they recommend that the allowable exposure time, T here is time, so I guess I'll make it lower T. Allowable exposure time in hours per day, this is going to be 8 divided by whatever that decibel level is, minus 90 divided by 5, and this is an exponent of 2. And this this thing, it has the units of this has the units of hours per day. So how many hours per day you're allowed to use a source that is greater than 90. So obviously if you're at 90, it's going to go all the way. If you're below 90, it's going to go all the way. We're not going to use this. But if you're over 90, go ahead and use this relation. Okay? The EPA is more stringent than OSHA, and says that the limit should be 70 decibels as the threshold. Where a worker would lose 5 decibels of hearing over 40 years for a typical 8-hour workday. That's what that threshold would mean. So you will lose 5 decibel of hearing over 40 years, assuming you're doing a typical work week of 8 hours per day. Okay, so this threshold is reduced to 65.2 decibels if you have a 24-hour exposure for 40 hours a week, for 40 years. So 24-hour exposure for over 40 years, you will lose 5 decibels. Okay, so reduction in noise pollution may be accomplished by isolating equipment, soundproofing rooms, housing the equipment separately, fitting motor with motor mutes, isolating vibration sources, and reduction in allowable ranges of state variables like pressure drops, rotational speeds, treatment volumes, etc. Okay, so let's look at 2 quick examples to see how this works. Okay, let's just do one example to do the effective one. Okay, so let's say I have 4 sources. I have a source, a sound source, and this is the intensity in decibels, or what's the L in decibels. Okay, and I have a TV, and that's gonna be 50 decibels. I have leaves being raked in the yard. Okay, and that's 20. I have a vacuum cleaner that's running around the house, that's 70, and I have a jet engine, because why not? I have 140 decibels. So here's a scenario. Determine the effective, L effective, that's what I'm asking for. L effective, when one is vacuuming one's carpet while the TV is on and the gardener outside is raking leaves and a jet engine is parked outside one's window. All right? So to determine the equivalent, equivalent decibel level, I will use the relation I had just shown you. This is going to be 10 log of the sources, each one of them basically like this, I to the n like that. So let's do that. It's fairly simple, I think. If you substitute all the values given from the table, just want to show you what happens. So 10 log of, well, I have 10 of the 50 decibel source from the TV divided by 10, plus 10 of the raking leaves stuff, plus 10 70, which is vacuum cleaner, plus the jet engine. If I put that all together, I get that, well, if you round it up, it's exactly 140 decibels, meaning that you basically don't hear anything except for that jet engine. You don't hear anything. It's drowning out all the noise, which probably makes sense. If you had a big airplane parked in your front yard and you're trying to listen to TV or do anything, you're not going to hear anything at all. It's all going to sound like nothing. You're just going to hear the jet engine.